Hello. How are you all doing? In this video, I'm going to solve in detail each of the math exercises that are included in this guide. This is the LUMNAM guide, which is for preparing for the entrance exam for undergraduate admission. This is specifically from the Biological, Chemical, and Health Sciences area. It should be mentioned that there are 120 questions in total here, but for mathematics, only questions 46 to 69 are included. So, as you can see, yes, there are quite a few exercises that I'm going to solve, so please, go get your notebook so you can take notes. And let's get started right away with solving the exercises. Exercise 46. A computer virus infected the hard drive. On the first day, it destroyed 2/3 of the hard drive. On the second day, it destroyed a quarter of what was left. Finally, on the third day, it destroyed 1/5 of what remained. The question is, what fraction of the hard drive was left undamaged? The first thing I'm going to do is say, what is the total capacity I have? I'm going to represent this with the letter X. So let me write here that this is the total capacity, considering then that X is the total capacity of the hard drive. So now let's start working on the solution and operations. It says, the computer virus attacked the hard drive, and on the first day, it destroyed 2/3 of the hard drive. So I'm going to write here, first day, we already know that on that first day it attacked, or rather, it destroyed 2/3 of the hard drive. So the operation I have to do would be X minus 2/3 of what? Well, of X, right? And here it's simple, because if I take away 2/3 of X from X, 1/3 of X, that is, of the total capacity. Here's what happened on the first day. Now let's move on to the second day and add it here. It says that on the second day, he destroyed a quarter of what was left. So, what was left? Well, 1/3 of X. So let's say that on the second day, the following will remain. We're going to have 1/3 of X. Okay, minus a quarter of what was left. 1/3 of X. So let's put minus a quarter of what was left. That is, 1/3 of X. And we do these operations. This 1/3 of X. For now, I'll leave it like that, and we'll solve it here. Multiply fractions by multiplying the numerators, 1 times 1 and denominators, 4 times 3, giving 1/12. And we leave the X there, done. In this case, since we have thirds and twelfths, we can convert them into twelfths. Convert this 1/3 into twelfths. That way, we can subtract homogeneous fractions, right? So, let's multiply both the numerator and denominator by 4y. Because I want us to have homogeneous fractions, so let's do it. 1 times 4 is 4 over 3 times 4, that's 12. What's the point? I want you to realize that 1/3 is equivalent to 4/12, right? Okay, I'll continue. I'll subtract 1/12 from this. And now we have a pretty simple operation. 4/12 of X minus 1/12 of X. So I end up with 3/12 of X in total. What have I simplified? If I divide by 3 twice, I get 1/4, right? Let me clarify. 1/4 of what? X? This was left after day 2, right? Now, on the third day, it says 1/5 of what was left was destroyed. So I'll note that here. Third day, well, on that third day, it destroyed 1/5 of what was left. So, from the remainder, which was 1/4 of X, are we going to subtract 1/5? Of what? From what's left, meaning 1/4 of X, we do something similar to what I did earlier. Okay, so come on, I'm going to do it over here. I'm going to set aside this 1/4 of X for now, and let's do it. Multiplying fractions. 1 times 1 equals 1 over 5 times 4, which is 20. What is X? We'll find a fraction equal to 1/4 using 20ths, so we can subtract directly. Here I can multiply by 5 and also by 5, so I can find the fraction equivalent to 1/4, but with 20ths. 1 times 5 is 5. We put that over 4 times 5, which is 20, and we write it down. We're going to subtract 20 from this. Here we go. All right. Well, we do it like this if we have Murata for creation it will go with soccer, with Mendoza, for whatever. You can keep dividing by 2 or simply divide the numerator by 4. Also, divide the denominator by 4. 4 divided by 4 is 1 in 45. And this here, well, it's already in x. So what we have at the end is 1/5 of x. So in the question that says, what fraction of the hard drive was left undamaged? Well, it's 1/5 of x. That is, 1/5 of the total capacity. Therefore, let's circle option D. Done, we're finished, that's it. So we've answered exercise 1. Let's go to exercise 46. 47 exercise. 47 says, when expanding x squared minus 3 and this to the third power, we get, and they also give us 4 possible answer choices. Look, this one can really be answered super quickly, because you should remember that when we have a binomial, whether it's raised to the second power, the third, the fourth, or the fifth power, always, if we have a negative sign here in the middle, then in the result, or in the expansion, the signs have to alternate, always starting with positive. So, since there's a negative here, necessarily in the expansion, we are going to have a polynomial with alternating signs, starting with positive. So let's see which one is like that. Notice here we have positive, negative, positive, positive. So the signs are not alternating, therefore the answer is not A. Let's look closely. Positive, positive, negative, positive. The signs are not alternating either, so that's not the correct answer either. Option C. Positive, well, here, positive, negative, positive, negative. That could be the answer, so I'll mark it. The last one is positive, but we've seen that's not it, right? So look, just like that, I already have that the correct answer is option C. It's done. But anyway, you're here to learn, so it's important that you also see how we can solve it, even if we don't use this little trick. I mean, what I'm saying is, what would happen if there were 2 options that also had alternating signs? Well, then we'd have to see what else we can do. Therefore, just doing what I just did right now wouldn't be enough, right? I mean, you have to know how to solve it. So come on, I'm going to show you how it's done. Look, here. We have to remember that when we have a binomial cubed, and also when we have a negative, the expansion should look like this. Let's write the first term cubed, then minus 3 times the product of the square of the first term by the second, then plus 3 times the product of the first term by the square of the second, and then minus the cube of the second term. Okay, that's for when we have a binomial cubed. In fact, this expansion comes from Pascal's triangle. So if you don't know how we get to this, please look up Pascal's triangle. Gregata. In that video, I showed exactly how to reach these expansions. All right, so once we have this, meaning once we remember the formula to expand a binomial cubed, we just need to expand what we have here. All right, so I get that x squared minus 3 all cubed should be, it says. Let's raise it to the third power first, but in this case it's x squared, so I'm going to raise x squared to the third power. Then it's minus, it says. Put a 3 then parentheses, put squared. But to that x squared, so I'm going to put x squared to the second power, right? Then this times b, but b is 3. And be careful, I'm only going to put the 3 and not the negative 3. The reason is I'm already adding the negative here. Then comes a plus. Then it's 3 times a times b squared, 3 times a. What did we say about x squared and b squared? So it's 3y squared, and then it's minus b cubed, minus 3y cubed, right? All right, so let's do these operations using the laws of exponents. X squared to the third power. Remember here, it's a power of a power, so I have to write the base and multiply the exponents. 2 times 3. That's 6 minus here. We have a 3, and here we have another 3, so I'll just multiply them right away. 3 times 3 is 9. Here we have x squared to the second power, so this would be x to the 2 times 2, right? That's 4. And this one should we continue? Next, in fact, look, here we have a 3, and it's squared, so I'm going to start with this square. 3 squared, that is 3 to the power of 2. That's 9 times 3, which is 27. So here it would be 27. I write x squared, and over here we also have y squared, and then we have minus 3 cubed. That would be 3 times 3 times 3, that's 27, right? And we also have a y cubed. Done. So would this be the solution then? As you can see, it's the same, right? Let's see. x6 minus 9, x4y plus 27, x2y2 minus 27y3. If we have everything, we're confirming the correct answer is C, as expected. Let's move on to the next one. How is this statement shown? Eduardo has a grams. Who knows of what? But he has a grams. Juan has a third of what Eduardo has, and Enrique has a fourth of twice what Eduardo has. The three together have less than 100 grams. How much more is needed to reach 1,000 grams? Okay, it's a bit confusing, but we can solve it, right? Let's see. I'm going to say that Ed, which will be Eduardo, is equal to OK. So what Eduardo has, then it says Juan, let's put a J. He has a third of what Eduardo has, so he has a third of what Eduardo has, but Eduardo has A, so Juan will have a third of A. Then it says Enrique. The fourth part of twice what Eduardo has is Enrique. It's equal to the fourth part of the double. Let's be careful with this. The fourth part of the double. That's why I write it this way. A fourth of twice what Eduardo has, and Eduardo has O. So, is this correct? If it's telling you that he has the fourth part of the double, it would be the same as saying he has the double of the fourth part. Okay. And the double of the fourth part is the same as half. Right. You can see it here, because you have a fourth times 2. A fourth times 2. That's 2 fourths of A, but 2 fourths simplified is just 1/2 of A. Right? And now, we already have what Eduardo has, what Juan has, and what Enrique has. They say we need to calculate what's missing to reach 100 grams. Sorry, I mean 1,000 grams. So what we would have to do is subtract what they have from the 1,000 grams. Between the three of them, when you add it up, they have A plus 1/3 of A and plus 1/2 of A, right? So, do they have this among the three of them? Then we write it down, and that should be the answer. Well, of course in grams, not in grams. Let's see where that is. 1,000? This one looks similar, but not here, I think. Let's see. 1,000 minus plus, divided by 3. Plus, divided by 2. Done. This would be the correct answer, which is option D. That's it. That one was easy, right? All right, let's go with the next exercise. Number 49, it says, find the values of x by solving x squared plus 3x plus 2 equals 0. Look, in this case, we can play a little with the answers. For the following reason, I want you to notice that this coefficient is positive, this one is positive, and this one is positive. I ask you, how would at least one of those three terms have to be for the sum to be 0? How would at least one of those three have to be? Well, at least one of those three has to be negative, necessarily, right? I mean, there's no way I can add 3 positives, get 0. There's no way, right? Therefore, necessarily at least one of these three must be negative. So, if you notice, if I substitute, for example, the values that are in part A, I mean, if I say, for example, that x is equal to 1, there's no way I can get 0, because I would have 1 plus 3 times 1 plus 2, that doesn't give 0. Obviously, it won't work if I put in a 2 either, because I'm adding positives, so the answers necessarily have to be negative. When solving a quadratic equation, there are 2 solutions, right? This one can't be because it has positives, nor can this one. This one could be since it has negatives, and this one could too, but not this one. So it's not option D either, so that's it. The correct answer is option C. We're done. That's all we have to do now. I know that right now while we're practicing, it's important for us to explore a little more to see. Well, first to make sure we're doing it right, but also so we can have different ways to solve the exercises. Not just in one way, right? We have time to solve it differently now, but during the exam, we really don't. If you see the answer is C during the exam, choose it and move on. Okay, well, now I'm going to solve this same exercise, but now I'm going to do it. Sorry, I'm going to do it using factoring. Let's see. Remember that to factor a trinomial like this, which has the form x squared plus bx plus c, we have to look for numbers that multiply to give us, in this case, and that when added, give us, in this case, 3. So think about which two numbers, when multiplied, give me 2, but when added, give me 3. Well, that's 2 and 1, right? 2 plus 1 is 3. 2 times 1 is 2. So, those are the numbers I'm going to use. Therefore, I'm going to separate this x squared as x times x. Now let's find the two numbers we mentioned earlier. Plus 2 and plus 1. 2 plus 1 equals 3. And 2 times 1 equals 2. They're correct now. Done. Now think about this. Look, we could solve for x from here, and it's pretty simple. That's it. Why is that? Because all of this can be divided, and so if I divide it, what would I get? X plus 2 equals 0, divided by something. But since 0 divided by anything is 0, x plus 2 equals 0. So I could say that x plus 2 equals 0. And from here, I solve for x. So x equals negative 2. Okay, this is already a value for x. Now also from this same expression, if I divide, what happens? X plus 1 equals 0, divided by something. But since 0 divided by anything is 0, x plus 1 equals 0. I would also set up another equation. X plus 1 equals 0. I'm telling you this because sometimes people just memorize to set each factor to 0. But that's why we do it. Exactly. Because when you move the other one to the other side by dividing, it cancels out. Okay, now I'm going to move this plus 1 by subtracting, so I get, by subtracting. So I get that x equals negative 1. We have both values. Whether this is x1 or x2 doesn't matter, right? So the solutions are negative 2. And negative 1, they're the same, right? Here they were the other way around, negative 1 and negative 2. But it's exactly the same. It's done. We've already solved exercise number 49. Let's move on to exercise number 50. I select the inequality whose solution is the set. And here we have a bracket. Negative 4/6, comma, infinity, and a bracket, right off the bat. You can't use a bracket here. You must use a parenthesis instead. Remember that, well, we can't reach infinity, so this has to be a parenthesis. That was a mistake. And also, there's another mistake here, which is this. Look, it shouldn't say inequality. Here, it should actually say inequation. When we have an inequation, well, these here are actually inequations. If we only had, for example, 5 less than 8, well, this here is an inequality. But the way the answers are here, they're actually inequations. Okay then? Well, this problem has quite a few mistakes, but it can still be answered. Okay, so again, let's select the inequation whose solution is, whose solution is the set. From negative 4/6, including negative 4/6, up to infinity. Look, that's it. Let's do it here. It's important that we first visualize what this refers to. I mean, what does it mean by negative 4/6 to infinity? And it's not hard to figure out. Look, I'm going to draw a number line, and we're going to put, for example, negative infinity over here, and infinity over here. Now let's put 0 somewhere. Let's say over here. And let's place negative 4/6. Negative 4/6 is negative 2/3. It would be slightly more negative. To the left of negative 0.5, it's not negative 2/6, but negative 0.6, or about 0.666, right? Well, the point is that it's to the left, right? Here we have negative 4/6. Okay, it's to the left of 0. Okay, now it's telling you that it's the interval that goes from negative 4/6 to infinity. And it's also telling you that it includes negative 4/6, right? That's why it has a bracket. So we're going to draw a circle, and we're going to fill it in. And now we're going to move, to the right. since it's saying it goes to infinity, okay? So all the values that satisfy that inequality are from minus 4/6 to infinity. So if I substitute, for example, a 0 in the inequality, it should work. And if I substitute, for example, a 100, let's suppose that here it should work. Why? Well, because it's supposed to work for all these values that I'm going to call x, for all of them. Okay, the ones that are in the interval given by the problem. So what I'm going to do is simply substitute a value as an example. I mean, a value that's easy. For example, I say that I'm going to substitute 0 because 0, well, because with 0, sorry, it's supposed to work. So let's go ahead and substitute a 0, okay? Where? Well, in all of these, to see which one fits. Come on, I'm going to do it here quickly, because it's easy, right? Here we go. We plug in 0. So minus 4 times. 0 is 0, making the whole thing 0. Now I just have minus 6. Dreacher 0, yes. Minus 6 is less than or equal to 0. So this works. Let's check the others. What's happening? If I plug in 0, I get 4 times 0 twice. There's 0. So everything here is 0 leaving 0 plus 6, which equals 6. Is 6 less than or equal to 0? No. So, does that mean this can't be the answer? I mean, that's not the inequality they're talking about? Is it clear now? Let's see. Let's try the other one. Here, for example, if I put a 0 here, it makes all of this become 0, right? All of this? So I get negative 2 Kochirk's 0, which is true. Negative 2 is less than or equal to 0, so I write 0 here. So 3 times 0 is 0. Then 0 plus 2 is 2, and 2 isn't less than or equal to 0. So it can't be a solution. So now we have two possible answer options. I want you to see that they're very similar. There's just a slight difference here, right? Here we have a 3, a 4, a 6, and a 2. The signs, however, are very interchangeable. Here's what I'll do next. It's to solve the inequalities, both A and C. Not all of them, because we already saw that B and D are not. So let's solve equation A. Let me rewrite it over here again, which is minus 4x minus 6 less than or equal to 0. And look, I'm going to take the liberty of solving it as if it were an equation. I'll write minus 4x less than or equal to. I'll move minus 6 as plus 6. And since minus 4 is multiplying, I'll divide by it. But there's a rule. There's a little rule that says, if you're going to multiply or divide by a negative, you have to flip the inequality. So in this case, we have to flip it. This less than or equal to sign becomes a greater than. Or equal to sign, we leave this 6 and this minus 4. So now we're going to move it. Now I'm just going to tidy this up a bit. It becomes, so x is greater than or equal to plus, divided by minus, minus. And here we have 6 over 4. Look, the answer looks similar. But here we didn't have x being greater than or equal to minus. 6 over 4, the answer was that x was greater than or equal to minus. 4 over 6, not minus 6 over 4. They look similar, but no, so this isn't the answer. So that's it. The correct answer has to be option D. Sorry, option C, right? Let's see. Anyway, I'm going to solve it so you can see that we have to reach that same solution. So, again, let me copy our inequality, and we're going to solve it following the same rules I just mentioned to you. So, do I write minus 3x with less than or equal to? We'll move the minus 2 over as plus 2. And since minus 3 is multiplying, we'll move it to the other side to divide. And also, since it's negative, we have to flip the inequality. So we get x is greater than or equal to 2 divided by minus 3. From here, we get that x is greater than or equal to plus divided by minus, which is minus, and we leave it as 2/3. Notice that even if it's not visible, this is already the solution. I'm multiplying both the numerator and denominator by 2. So 2 times 2 is 4 over 3 times 2, which is 6. That x is greater than or equal to negative 4/6, and that's what the graph shows here, right? X is greater than or equal to negative 4/6. So if that's correct, then the right answer is, in fact, option C. That's it. We're done. Let's go. With exercise number 51, solve the following system of equations. Here we have the system, and they give us 4 possible answer choices. Look, here we start by seeing what is convenient to solve. Let me explain what I mean by that when I say what is convenient for us to solve. I'm telling you this because many times people just come in and try to apply some method without really noticing what would be simpler or faster. Here, for example, one of the quick methods would be elimination, which is also known as the addition and subtraction method, or the reduction method. But there are many people who say, well, first I'm going to eliminate the x's. Wait a minute, it's not necessary to eliminate the x's first. Also, here, in order to eliminate the x's using this method, it's not necessary. Well, the truth is that it is quite complicated. Well, not very. But it is more complicated. It would be much easier to eliminate the y's first. Why is that? Because I could multiply. Let me show it in red. I could multiply the second equation, for example, by 5, and if I multiply the second equation by 5, I want you to notice that we can already eliminate the y's, and it would be much faster, right? So if I eliminate the y's, can I already know the value of x? And if I can know the value of x, I may already have the answer. So let's see. Come on. Let's move forward. So I'm going to copy the 3x plus 5. Sorry, that's the one they're giving me here, equals 7. Next, we multiply the second equation by 55. By 2x, it's 10x. Then 5 times minus is minus 5. And on the right side, we have 5 times minus 4, which is minus 20. In this case, it's better for me to add the 2 equations, since these 2 signs are different. All right, let's do the operations. I get 3x plus 10x, which is 3x in total. Then we have 5y plus minus 5y. So those cancel out, and on the right side, we have 7 plus minus 20 and minus 20. Well, that's minus 13, right? Finally, we have that x equals minus 13 divided by this 13, which is going to be divided. And well, minus 13 divided by 13 is equal to minus 1. X must be negative 1. That's it. The correct answer is option C, since it's the only one with it. X equals minus 1 here, minus 2 there, and 1 here. So none of these are solutions? Let's see. It should be that when I substitute the value I found for x into either of these 2 equations, it gives me the value of y, right? It has to give me that. If not, then it means I'm wrong. Let's see. I'm going to substitute, for example, in the first one. Okay, it's not that simple, but let's substitute there. So I have 3 times the value of x, which is minus 1, plus 5 times y equals 7. Look, I'm substituting. Here I do the operations. 3 times minus 1 gives me minus 3 plus 5y equals 7. This minus 3. We add it to the other side, so 5y equals 7 plus 3, which is 10 now. Do we divide by 5? So I get that y equals 10 divided by 5y, and well, that's 2. So y equals 2. And look, we also had that. Y equals 2. All right, that's simple, right? Let's move on to exercise 52. This one will take a bit longer, but don't get impatient, because I'm going to say several things that I think are absolutely necessary for you to keep in mind. It says, determine the range of the function f of x equals 5 minus 3 times the quantity x minus 2 squared. Let's see. I'm going to start by making a small sketch of the graph. Allow me. I'll do it over here. Well, I'm going to draw the Cartesian plane first, and then I'll make a sketch of the graph. What I want is for you to first understand what the range is, because we're going to be talking about domain and range in some exercises. So, I'm going to explain to you right now what the domain is and what the range is, even if it's in very simple terms, and also, even if it's in terms that are not necessarily very, what word should I use? Like, very formal. Well, what I'm going to say won't be very formal. Okay. But it will help you to be able to solve your exam. Look, imagine that you have, for example, this curve. Well, let's suppose I want it to end here. There it is. We have this curve like this. Let me put some numbers here, just so you can see how far it's going. So, first we have minus 1. Well, I'm going to put a scale here. Here it's 1, and here it's 1. Okay, so here it would be -1, -2, -3, -4, -5. So this one goes up to -5. Okay, this is an important value. I also need the value that it reaches up here. So it would be 1, 2, 3, 4, 5, 6, and 7. So there's a 7 here. I also need the value that it reaches down here. So let's suppose it only goes up to here and then comes back. So we have 1, and then come on, 2, and to the right, 1, 2, 3, 4, 5, 6, 7, 8. So here it would go up to 8. All right, so there are some important values. Because I insist, what I want is for you to at least have an idea of what the domain is, and God, the range. Look, in very simple terms, the domain is going to be that interval of values that the function can take. Okay, in x, sorry, it's the interval, sorry, of values of x that the function can take. And the range is that interval of values. From y's perspective, that's what the function can take. What do I mean? Look, you see that the function with respect to x, I'm going to stand here with respect to x. So, am I going to look up or am I going to look down? This function starts from -5. But I can keep walking this way, and whenever I turn, I'm going to find the function. Now, whenever I look up or down, at the moment I get here, I'm not going to look up anymore. But I'm going to look down and I keep finding the function. So, I keep walking. I keep walking here. I stop looking down. I start walking again, looking up, sorry. And I keep looking up and I keep finding the function. That's it, just up to here. Well, the domain is going to be exactly that. It's the interval of values with respect to x, okay? That is, walking along the x-axis and looking up and looking down, in which I can see the function. Therefore, when they ask you for the domain, you have to do the following. Imagine that you're going to draw a lot of lines. Let me erase this quickly. You're going to draw a lot of lines, but vertical ones. And you're going to pay attention to which interval. If you touch the function, that's your domain. For example, if I draw like this, I'm not touching the function. Or, well, I'm not touching the curve here either. And over here, I'm not touching it anymore. But I know that if I start from 5 there, it does touch it. And up to where at most? Well, from -5, sorry. And up to where at most? Up to 8. That's the domain. This interval is the domain from x's view, so remember that. Therefore, the domain, in this case, is going to be that set of values that goes from -5, including 5, up to 8, including 8. That's why I use brackets for the domain. Now, what's the range? It's quite similar. Now, the difference is that you're going to move along the y-axis. Imagine you have a basement, with one staircase going down and another going up. Now, the difference is that you're not going to look up and down, but you're going to look to the right and to the left, okay? So come here, you look to the right, you see the function, you keep climbing, and you turn and see the function. Or, well, the curve keeps going up, and you turn to the right and to the left, to the left. If there's a function, keep going, you keep going here. If there is, see that there is, keep going, you keep going. And up to here there is. But after that, if you go up a little more, here, you don't find anything anymore, on either side. Therefore, it means that you can't go any further, you can only reach up to there. Up to what maximum value? Well, up to 7, right? Now, the minimum, up to what value could you go down and still see the function? Well, at minimum, down to -2. That's the range. So for the range, what I do is draw lines that are more or less horizontal. And if I come across the green curve, then it means it's part of the range. So, where does the range start and where will it end? For this graph, which I'm making up pretty well, then it has to go from -2 to +7, right? Because -2 is the smallest value I can look at, while the largest value I can look at, regarding the axis of the e. And don't forget, it's 7, so look, here's -2, and over here is 7. All right. So in this case, the range would go from -2 to 7, that's it. That would be, in very general terms, the range. With this information, we can now solve these types of problems. I'm going to make another Cartesian plane, because I already messed up this one with that drawing. But I wanted you to understand this part first before we start doing the exercises, because otherwise, well, that's it. I could give you a formula, but that's not my goal. That's it, because I really want you to understand how I'm solving each of the exercises. Obviously, I'm not going to teach you everything in this video, which might last an hour or two. I'm not going to teach you all of mathematics. It's impossible, right? But at least the topics that are related to this guide, I'll try to explain them as best as I can. Look, I'm going to put it here again. Studies show that it's organic, that Dwayne's is the same way. Creation on Friday. Did it mess you up too? Which girlfriend is more strict? More than playing soccer, right? I should have gone through the mock 1, but it didn't work out. Don't worry about it, okay? What I want is for you to simply realize that I am representing the function f of x equals x squared for now, like this. Okay, now what I want is for us to make some modifications to this function. For example, what would happen if instead of having f of x equals x squared, we had f of x equals negative x squared? Very simple. What happens is that it gets inverted. I mean, instead of having it like this, facing up, now it's going to be, well, I can't really show it, but facing down, so we're going to invert it downward. So, picture this. The drawing would look like if I put a mirror here and it just reflected. So this is the graph of the function negative x squared. Okay, don't forget that. Now let's look at something else. What would happen if now I have f of x equals, I open parentheses and put x plus 3 and raise it to the power of 2? Well, in this case, what's going to happen is that the graph will shift 3 units to the left. Careful left! When I add inside the parentheses, I'm going to shift the function, well, the graph, the function 3 units, but to the left. In the case that I subtract, careful, in the case that I subtract, I shift it to the right. So, since here we have x plus 3, it means it's shifting. 3 units to the left. 1, 2, 3. Which one is shifting? The green one, the x squared one. So it would look like this? Look, well, again it turned out ugly. But something like that is fine. And I'm missing one more thing. Now, imagine that we have f of x equals x squared plus 3. If we're adding outside, meaning it's not inside the parentheses like here, what we're going to do is take our original graph, which was x squared, and now we're going to move it up. The number of units it says there, in this case, it says plus 3. So it's going to go up 3 units. So I'm going to move this green one up 1, 2, and 3 units, and then I'll redraw the green graph. Okay. So, I want you to see here in general everything I'm saying. Look, this is the original one. If it's negative, we flip it. If we add, then it moves to the left by the number of units, as it says here. If we subtract inside the parenthesis, it shifts to the right. Remember, if you add, it goes left. If you subtract, it goes right, as long as it's inside the parenthesis. Okay, now, what happens if you add outside? It goes up. What happens if you subtract outside? So, if we had x squared minus 3, then it goes down 3 units. And here we draw it. And also, one more thing that I'm still missing is, what would happen? Let's see. I'll write in black. What would happen if we had f of x equal to 10x squared? Well, in this case, what we're going to do is that the graph of the parabola is going to get compressed. Instead of this, watch my hands. This will happen, okay? So, the larger that coefficient is, for example, if it were 30 or 40, then we're going to keep compressing it more and more. So, in this case, we're going to compress our original graph, which was the green one. Let's suppose it would end up being something very compressed. For example, something like this. Okay. And remember, the larger this value is, the more it gets compressed. Now it could also be stretched, meaning it could be a little wider. That would be if the values range from 0 without touching 0 up to 1 without touching 1. What do I mean by that? For example, if it were f of x equals 0, 0, 2x squared in this case, this red parabola, green, would have to be made a bit fatter, meaning it would be stretched. Okay, well, With all these scribbles, now we're finally ready to graph our function. Obviously, it's not always necessary, but we do need to make the graph to solve this exercise. In other words, this one, no. But was it necessary for you to know how we can visualize the quadratic function? Because possibly, you might get another exercise where you do have to use all this knowledge I just shared with you. Let's make a sketch, okay? Check out everything it has. First, we start with, well, not this one. This number adds 5 even at the start. Putting it here, 3 plus x squared equals x squared plus 3, right? So, since there's a 5 outside, what does that mean? It means the vertex, or the whole parabola, moved up, right? By how much? Well, 5 units, so come on, let's mark 5 up. 1, 2, 3, 4, 5. So it goes around here, right? Ready? Now notice that it has this negative, which is the coefficient of this minus 3. So it would be more or less like what I have here. What does that mean? Well, that it goes downward, right? In other words, its branches extend downward. The parabola should look like this, right? We'll draw it soon. What else? There's a minus 3. What does that mean? It means it's a bit squished, right? But is that really not going to interfere with the answer to the exercise? But this does, right? Because here it's telling you that it's x minus 2. What does x minus 2 mean? Ah, well, it means that it's shifted 2 units. To where? To the right, right? So to the right, I move 2 units. I'm going to put the 2 right here. So the vertex is going to have coordinates. Let me put it here, even though it's not asking 2, 5, right? What else do we know? We know the graph will go downward and be narrower because of the 3. All right, we have it. So the graph of this function. Obviously, it's not turning out so nice for me, right? But if you go into GeoGebra and enter this exact function, it should give you a graph very similar to the one I'm showing you. Take a look at this, in case the graph isn't really clear to you. Well, it's always going to go down, okay? Always going to go down. So it's going to come from negative infinity, really to infinity. And it won't touch the end. It just keeps going up, 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 up. And how far does it go? Up to 5 at most. Therefore, the solution would be, sorry, here we use a bracket, because it can touch that value. So the interval would be from negative infinity to 5. We can also express this in another way, right? If I'm saying it goes from negative infinity to 5, what does this imply? Well, that it has to be less than or can be equal to whom? Well, to 5, right? That is, it's all the values that are smaller or equal to 5. So from here down are the values that the range of the function will take. Okay. So the correct answer is y equals, y less than, or equal to 5. So that's the correct option, right? Y less than or equal to 5. All right, we're done. The next ones will be easier. Because even though they're also about domain and range, since I already explained a little bit about what that's about, I think we can move forward, right? Let's see, again. I won't explain domain and range again, but I'll briefly describe the graph of the sine function. And also, well, cosine in this case. And I'll also briefly explain how each of these parameters will affect it. I mean, what happens if I change the 2? What happens if I change the minus 3? What happens if I change the 5? It's really going to be very similar to what we just did, okay? Look, the graph of the cosine function is more or less like this. It starts here. Or rather, it doesn't really have a beginning, but it's something like this. Look, it oscillates. It's not coming out very nicely, but imagine something like this. And it also oscillates on this side. It goes down to -1, goes up to 1. It goes down to -1, goes up to 1. From -1 to 1, it keeps repeating this. So that would be the graph of the function f of x, equal to cosine of x, cosine of x. Okay, now again, what would happen? If I have, for example, a negative, I mean, just the negative itself, well, something very similar happens. Again, instead of starting up here, I'm going to start down here. So it would be like this, but reversed, right? That would be the reflection. That's what would happen. If we have the graph of the function f of x equals negative cosine of x, I'm going to remove it, but just so you know that's what it is, okay? It simply gets inverted. So, what else? Over here, we have this 3. This 3 is important for solving this problem. Look, if we just have f of x equals cosine of x, I mean just one cosine of x, then we draw this graph. But what if we had 2 cosine of x? Instead of the crest reaching 1 and minus 1, see, here's minus 1 and here's 1. If it were 2 cosine of x, the graph would go up to 2 and down to minus 2. Just imagine it stretches. Since we change the amplitude, that's what we call it. So, if I have a 3, what does that mean? Well, it means that the graph will go up to 3 at most, but also, at minimum, it will go down to minus 3. That's what this 3 means. So, now we have a little more information, right? Now we know that it has to be inverted, and we also know that just because of what I have here. It'll range from minus 3 to plus 3, but over a wider span, right? Now, what happens, for example, with this 2 right here, what it really means is that it increases the frequency. If I had cosine of x, it would look like this. But what about cosine of 2x? What it really does is that the waves go, well, faster. Right. Or they appear more times. That's why I say it increases the frequency. And if I had, for example, cosine of 10x, picture a bunch of waves coming out, okay? So, as I increase it more, well, maybe I shouldn't exaggerate so much, but imagine more. So as I increase this number here, this one right here, then there will be more waves. Obviously, for the purposes of this exercise, it's irrelevant. I mean, this could be an 8x, and the answer would still be the same. Why? Because all that does is change the frequency. But it doesn't give me any more information. But something that does give me information is this 5. And that 5 does exactly the same thing as it did in the parabola we saw. What's it going to raise? Well, the whole graph. Which one? The one I'm already imagining, right? I mean, it's inverted. It goes 3 down and 3 up from its center. And well, in this case, it's shifted up, right? So, let me try to draw it. It won't look very nice, but just imagine it like this. I'm going to use yellow to draw a new axis. What do I mean by that? Right now, it's oscillating at 0, right? I mean, on the x-axis, it goes up 1 with respect to x, then down, up, down, and so on, right? But always taking the x-axis as a reference. But since in this case, we already saw that it's going to go up 5 units, I'm going to draw a line at 5, and this time I'll use yellow. I won't have much space here, so let me move this down a bit so you can see it. And let me go ahead and mark everything. We have 1, 2, 3. Sorry, 1, 2, 3, 4, 5. Here was already 5, 6, 7, 8. Let's see. I'm marking up to 8 because I already know that from this 5, I have to go up 3 and then go down 3. Right? That's why I'm marking that 8. I'm going to do it in blue, so let's see if it turns out nice. Okay, here we go then. Taking all that into account, now I'm going to oscillate at 5. That's where we left off. It has to be a minus 3, so instead of starting up here and going down, I have to start down here and go up. Okay, but I have to go down 3 from here because of this 3. So it would be 1, 2, 3. From here, then I'm going to start oscillating. Also, since the frequency is a bit higher, I'll do it now. It can only go up to 8, right? That's because it needs to increase by 3 from 5. So it should look like this. Look, it should be a little curve that goes up to 8, then down, then up, then down. It's turning out terrible, isn't it? But anyway, I think you get the idea. Here it's the same. I go up to here, up to 8 down, up. Well, there it is, more or less, right? So now let's calculate the range. Let's see which is the smallest value. Which one I can see. With respect to the 10 axis, again, I look to the right and I look to the left, right? To be able to see the range, I'm going to start with the range. In this case, it would have to be from here, which is 1, 2, up to what number? Let's see. 3 yes, 4 yes. I mean, on both sides I find a function. 5 as well, 6 as well, 7 as well, 8 as well. And that's it, right? So it has to go from 2 to 8. Therefore, my range will be those that belong to the set of real numbers from 2 to 8. This is my range. Let's see. I don't know if we've already answered the question with that. Yes, with that. Look, the correct answer is option D. Look, here it is. It's the interval of values that goes from 2 to 8, obviously including 2 and including 8. It's right here. Something important to tell you as well is that the domain, as you can see, is basically the same. Well, not here. Here, they're putting something else. If it goes from negative infinity to negative infinity, that's incorrect, right? Notice that in the others, it says they go from negative to positive infinity. Why? Because these graphs, let me go back to this one. This will always be this way. It never ends. And it's the same here, and with the one we have too. So, really, the domain, for the sine function, cosine function, is going to be plus or minus infinity, okay? For the tangent function as well, it does change, because there are things called asymptotes. So if you want to look into that a bit more, I already have videos where I explain the graph of the tangent function. All right, that's it. We're done with this exercise. I'll make a quick adjustment, then let's move on to exercise 54. Again, we have something that has to do with trigonometric functions, it says. Choose the function with a phase shift of pi units to the right. We just saw that, right? Which one is it if it says pi units to the right? What does that mean? Inside the parentheses, is it adding or subtracting? I mean, if we had x, it says it's to the right. If I want it to move to the right, what do? I subtract, right? Inside the parentheses, what do I have for sine? It's pretty far away. I think I moved it too far. Sine of x minus pi. Why minus pi? Because it's shifted right by pi units. So it should look like this, right? So the answer is sine of x minus pi, correct? Is that option C? Let's see. Anyway, just to make it really clear how each of these parameters we're moving here affects things, let's do a quick review to see how this one here affects it. I mean, what really changes? Well, remember that if we have it inside the parentheses and it's multiplying, what changes there? In that case, it's going to change the frequency. So, if we had the graph of the sine function of pi x, the only thing we would see is that this makes it go much faster, right? I mean, it increases the frequency. Now, what happens in this case? If we have sine of x plus p, since we're adding pi, that means it shifts to the left. Okay, but we want it to go right here. So that was the correct answer, right? Finally, what about this one? Here, we're multiplying the sine of x by pi. So what this would do, let me show you here. The thing is, the function would be wider, right? Or, well, taller. It's going to stretch. I mean, we change the amplitude, right? And so, as you can see, each of these parameters, I'll call them that, affects the function in a different way. So, the one that shifts it, to the right, is definitely option C. Okay? I mean, where I'm subtracting inside the parenthesis. All right, let's move on to exercise number 55, which is once again a function. Let's see here. Again, I'm not going to explain the domain and range in detail anymore, but I do want to remind you, at least briefly, what does the graph of the function e to the x look like? For this? So, once again, let me quickly sketch a graph. Look, I'm going to put the x-axis and the y-axis here, and I'm going to graph. Well, at least I'm going to try to graph the function f of x equal to e to the x. See, that's a line. Or, well, it's a curve that stays very close, but really, really close to the x-axis, and little by little it starts moving away. As it passes here, it moves through 0, 1, and then rises. It actually turned out well, didn't it? So this is the sketch of the graph f of x equals e to the x. Now, what happens if we, for example, set f of x equal to e to the 2x, or e to the 5x, or e to the 5x plus pi, or things like that? What would really be happening is just that it would change how fast it grows. I mean, I could have another function, for example, very similar, but maybe this one goes up faster over here. Okay? or maybe it's flatter. That's the only thing that's going to change. But really, regarding the range, nothing would change if we only move the exponent. What is it that will actually change when you want to? Sorry? What is it that does change and actually affects your answer in that case? Well, the only thing that does affect your answer is this 4y. Because this 4, remember what it does, is what? Since it's outside and positive, it shifts the whole graph up by 4 units, right? So what I'm going to do, let me erase this, is now put a new one. A new x-axis, sorry, but I'm not going to put it here. I mean, on the x-axis again, but I'm going to move it up. Right. By how much? I have 4 units. 1, 2, 3, 4. Here's where I'll place my new x-axis. Let's see. 1, 2, 3, 4. Over here. Okay, so I'm doing it this way. Not because I'm literally going up the x-axis, but because this is going to be my reference line, where I'm going to draw this green line again. So, let's do it again. Sorry, this green curve, in this case, I'm going to draw it in blue. And so, it would look something like this. It turned out uglier, right? But anyway, this one here would already be f of x equals e to the x plus 4. Okay, now, the domain of this function that I have is exactly the same as the domain of this function that I have, because I insist, what's up here really doesn't affect the range. And how did we find it? Again, what we had to do was go to our ladder and see from where. Now we start to see the function. In this case, as you can see, I start to see it from 4, right? Or do I start to see it here, even if it doesn't touch it? From there, I already start to see it. Until where? To infinity. Since I can keep going up, even if I turn to the right, I still see the curve, right? In this case, to the right. It would have to be this interval that goes from 4 to infinity. For infinity, we always use parentheses, but think about 4, what do I use? Parenthesis or bracket? Remember that a parenthesis means it doesn't touch it, and a bracket means it does touch it. In this case, we'll use a parenthesis. Why is that? Well, because it doesn't touch it, so I use a parenthesis. I write 4, then a comma, then infinity, and I also use a parenthesis. This is the correct interval, so the correct answer is option B, right? There you go. This would be the correct answer. All right, we're done. Look here again. You could have ruled out some things, because you already had a bit of experience with what I just told you. No, because if you know it went up by 4 units, then this didn't make sense, and neither did this 1/4. Now, it didn't make sense for it to be 1/4 either. And besides, with a bracket? So, the only one that could make sense was option B. But obviously, you have to know what I've already been telling you, right? Okay, let's continue then and move on to exercise number 56. It says, the midpoint of the segment that joins the points A2mm plus 1 and B2mm minus 1 is. Look, in this case, since we're talking about segments, I want you to notice that this value and this value are exactly the same. What does it mean then that if I say that with respect to x, this point has coordinates 2m something I don't care about, and this point with respect to x should also have coordinates 2m comma something, right? Now, if I want to find the midpoint, this midpoint with respect to x also has to be at 2m comma something, right? And in this case, the only one that has 2m at the beginning is option C. That's it, we're done. I mean, necessarily, the midpoint also had to have a 2m at the beginning. Okay, why? Because these two now have a 2m too. But how can we be sure that, for example, in fact, the other point, sorry, the value of y is actually m? Well, we can do it in a different way. For example, something that comes to mind to do quickly is simply an average, right? I mean, I could take m plus 1 and add m minus 1 to it. And this has to be divided by 2. Why am I going to take an average? Well, because if I take an average, what I actually find is the number that's in the middle. So that's what I'm going to do. We add m plus 1 and m minus 1, the ones cancel. Leaving 2m dividing by 2 cancels the 2's. So we're left with m. So, as you can see, If I get 6 feet 6 inches m, that's it. That's all I need to do. Simple, right? Let's move on to exercise 57. Which of the following lines has the same abscissa value with respect to the origin as the line y minus 4x plus 1 equals 0? All right. In this case, let me quickly draw a Cartesian plane, because I need you to understand well before I give you the method for what I'm going to do. Because obviously I could just tell you, look, just do this and that's it. But I need you to understand what we're doing. So, I'm going to draw any line, for example, this one. It's important for you to remember that this axis is called the x-axis, right? And this one is called the y-axis. Also, this point here, where it crosses the y-axis. You agree it's called the y-intercept, so that must mean something to you, right? This is the y-intercept. At this point, you'll agree with me that x equals 0. I mean, I don't know what y is, but x is 0. Right? At this point, I'm pretty sure that that what? Well, that y equals 0, right? Why is that? Here, it would be something like 0, 0, since it's on the axis. Well, it turns out that this problem is referring exactly to this point. Look, it says, which of the following lines has the same abscissa value with respect to the origin? Look, the same abscissa value with respect to the origin. So, it's referring exactly to this point, where it crosses the x-axis? Is that what it's referring to? Whose? Well, from this line then. What do I have to do? Oh well, I'm going to go to my line, and I have to set something equal to 0. To whom? Well, to y, because I want to find this right here. I mean, this little point, so come on, let's do it. In this case, then I would have y, but I'm going to change it to a 0. Minus 4x plus 1 equals 0. Now, to solve for x, just move the plus 1 to the other side as minus 1. So I have 4x equals 1. Now we solve for 4. Sorry, moving it over by dividing, I get negative 1 over negative 4, since dividing two negatives gives a positive, x equals 1/4. Does that mean then that, well, I'm even going to remove it so it doesn't bother you? It means that the graph I have here, or, well, the line I have here, is going to cross where? Well, it's going to cross at 1/4, 0. Why? Because I'm saying that when y is 0, x is 1/4. So the coordinate would have to be 1/4, 0. That's where it crosses the x-axis. So we have to see which of these also has that same crossing point. That's what we're going to look for. So, come on, let's do it quickly here and see how fast we can find it. Come on, you can even do it in your head, right? Let's see. I put a 0 here, and then this minus 1 would be added. So I'd have 1, and this minus 4 here would be dividing. So I'd have 1 over minus 4, that would be minus 1/4. So, no. Again, we set this to 0. This one would be subtracted. So I'd have 4x equals minus 1. And that 4 would divide, so I'd have x equals negative 1 over 4. So we don't set y to 0 either. We move the 1 to the other side, adding, well, this is going to be true. Look, so what do I get then? 4x equals. Move the minus 1 over by adding, then divide by 4. And as you can see, this one does make us arrive at the same value of x. So in this case, we do have the same value of abscissa with respect to the origin. Therefore, the answer would be option C. That's it, we're done. Look, if this wasn't completely clear to you, which is totally logical, or it might seem illogical, but it's understandable if it's not clear to you. The first one. Anyway, I recommend that right here on YouTube, you search for Complete Course Analytic Geometry Grahera. All of that. Complete Course Analytic Geometry Grahera. And a course will show up for you. I have 67 videos that are already organized. I mean, from general concepts to equations of the line, circle, ellipse, parabola, hyperbola, etc. I already have all the materials you need to learn analytic geometry in detail. And honestly, analytic geometry problems are the ones that can cause the most trouble for students in this type of exam. More than calculus, since I think it's less complex on these exams. Let's do exercise 58. Find the distance from the point -1, 1, to the line -3, x plus 4y minus 8 equals 0. For example, this one. In this case, you absolutely have to remember a formula here. I'll write it down for you, but it's important that you know it by heart. The formula says that the distance is equal to the absolute value of a times x1 plus b times y1 well. This is a 1 and plus c. Then we close the absolute value. Let me shorten this line a little bit more. Well, and that's going to be divided by the square root of a squared plus b squared. All right, where does all this come from? Well, it's very simple. Remember that the equation of a line in its general form has the following form. It's x plus b plus c equals 0. As you can see, I already have the values for a, b, and c, right? Now, where do I get the x1 and y1 from? Well, here they are. Look, it's this point. I mean, it has coordinates x1, y1, so I already have everything, right? So we're just going to substitute. So now I have that the distance is equal to the absolute value of what? Well, of which is -3. I'll write it multiplying x1, which is -1 plus b, times y. Well, b times y1 is 4. So here I put 4 times y, 1, which is 1. And to this we're going to add c, but c is equal to -8. So this is correct, right? Let's extend the line and add the equals sign. Sorry, I forgot to close the absolute value. Now this is going to be divided by the square root of a squared plus b squared. So in this case, it was -3 squared plus b squared, which was 4 squared. Like this, right? Okay, let's continue with this. So I get the absolute value of -3 times -1 is 3 plus 4 times. 1 is 4 plus times, minus is minus. What? 8. I close the absolute value. We draw the line, and this is going to be divided by the square root of -3 squared, which is 9 plus 4 squared, which is 16. Let's continue over here. So I have that the distance is equal to the absolute value, again, of 3 plus $4, which is $7 and 7 minus 8 is equal to -1. So I end up with the absolute value of -1. And down here, we have the square root of 9 plus 16, that is, the square root of 25. Let's continue. The absolute value of -1 is 1 over the square root of 25, which is 5, and 1 divided by 5 is 0.2. Would this be the solution? That's right. So the correct answer is option A. All right, we're done. Let's move on to exercise 59. There are 69 in total. We still have several left, but we're making progress. Considering the circle as a geometric locus, what algebraic expression do the coordinates of points P, X satisfy if their distance from the origin is 10? Okay, that one is also easy. I don't really like the wording, but I understand what it means. But basically what it's telling you is that you have a circle with its center at the origin. Okay, so let's draw it. It won't look perfect, but just imagine it's a circle centered at the origin. Something like this, okay? And it's asking you, which of those has the property that the coordinates of the points x and y have a distance of 10 from the origin? Meaning that from here to here, it's 10. As you can see, this distance is really what? Well, it's the radius, right? Now I'm going to ask you right away. Tell me how much the radius squared is worth. Well, it's 100, right? Why am I asking you this? Because in the formula for the equation of a circle with its center at the origin, we have that x squared, that x squared plus y squared equals r squared. So in this case, I already asked you for r, and also r squared. So we have everything. So I get x squared plus y squared equals r squared. It's equal to 100. But here we don't have the solution immediately, since not everything is set to 0. So we're going to move that 100 by subtracting it. So I end up with x squared plus y squared minus 100 equals 0. And that's it. That's option C, right? X squared plus y squared minus 100 equals 0. That's the solution. As you can see, this one was pretty simple. Let's move on to number 60, which isn't so easy anymore, so let's do it slowly. It says, the equation of the parabola with vertex at V3, for parameter p equal to 5, and focal axis parallel to the axis. And let's see, there are several things here that are important to highlight. For example, it's talking about the vertex, it's talking about parameter p, and is it also talking about the focal axis? Let me tell you what each of those things is, in case you didn't know them or just don't remember them. So, once again, let's put a little graph here, or, well, a Cartesian plane, so we can plot. Look, right off the bat, it's telling you that the vertex is at 3, 4. I'm going to put it here. Okay, 1, 2, 3. 1, 2, 3, 4. So the vertex will be around here at 3, 4. Now, an important thing here is that it's saying the focal axis is parallel to the axis. And what does that imply? It means we have a vertical parabola. Why? The focal axis is a line passing through both the vertex and focus. So if the vertex were over here, if the focus were over here, then the focal axis would be like this. Now, if the focus were, for example, over here, let me change it. For example, over here. So, the focal axis would go like this in those two cases. As you can see, we would have the focal axis parallel to the y-axis. And, in those two cases, that is, whether the focus is above or below the vertex. What would happen, for example, if I focused here? In that case, the focal axis wouldn't be parallel to the y-axis, and therefore, necessarily, according to the information given in the problem, necessarily, the focus has to be either above or below the vertex, right? So that the focal axis can be parallel to the y-axis. Are you following me with that? Right? Great. Now it's telling you parameter p is 5. So what is parameter p? It's simple. The parameter p is the distance from the vertex to the focus. Careful. Here the sign does matter. It's the distance from the vertex to the focus, not from the focus to the vertex, from the vertex to the focus. If it's telling you that this parameter is 5, then it means it's upwards. If it told you that the parameter p is -5, then it would go downwards. In this case, then we have that above the vertex. That is, 5 units. The focus will be above. 1, 2, 3, 4, 5. Here, the focus is ready. With this information, we can draw our parabola. Remember, a parabola always surrounds the focus. So, it should be like this, right? Well, this information I just gave you was really only useful for knowing that we're dealing with a vertical parabola. It really didn't matter if it went down or up. But I did need to know that it was vertical. Why do I need to know that? Well, because I'm going to give you the equation of the parabola next, but vertical. In this case, we're going to write it. Next, we write x minus h squared equals 4p times y minus k. This right here is already the vertical equation of the parabola. Okay, when the vertex isn't at the origin, it's at any point on the plane. Now, what are h and k? It's very simple. The vertex has coordinates h, k, so h is 3 and k is 4. We do everything, right? Let's substitute. I have x minus h and h is 3. So we put it squared, it's equal to 4 times p, but p, this parameter, right? It's 5. Remember that it's the distance from the vertex to the focus. That will also be useful for you, surely, for another exercise. It multiplies y minus k, so in this case, y minus 4. Here we have a binomial squared to expand. Square the first term, then subtract twice the product of the first and second. That is, 2 times x times 3, which gives me 6x, and plus the square of the second, that is, the square of 3, which is 9. On the right, 4 times 5 is 20 times y gives 20y. Then minus 4 times 5, which is 20, and 20 times 4 equals 80, right? Now we'll move the minus 80 to the other side as a plus. So I have x squared minus 6x. Then move 20y as minus 20y, and also plus 9. We're going to add it to this plus 80 since it's going to be added. so I'll have plus 89. And well, on the right side, we have a 0 now. So the correct answer should be x squared minus 6x minus 20y plus 89 equals 0. Which, as far as I know, is this one, right? Option A, let's see. Anyway, let me double check quickly, just in case I made a mistake in any of the steps. Because the process, as you can see, was a bit long, right? Here it says in the guide that the correct answer has to be D. So yes, everything's good. It's done. So this exercise is finished too. Let's move on to exercise number 61, which says geometric locus in the plane of any point, where the total distance to two fixed points, known as foci, remains constant. Is this really a definition? I can't say much now. Maybe I can make a small drawing for you, but there's not much to show. The correct answer is parabola. Sorry, that's not true. Ellipse, that's the correct answer. So why do I say it's ellipse? Look, in an ellipse, the following has to happen. I'm going to draw any ellipse. It's going to look a little bad, sorry, but I need to show you something. Let's draw the ellipse. It's not too bad. It's about here. There we go, more or less, okay? The ellipse is precisely that geometric place in the plane where the sum of the distances to two fixed points called foci is a constant amount. That's the definition of an ellipse. So, you just had to learn it. But I'm going to tell you what all that means. Look, let's suppose we have the foci here. I'm going to say this one is F and this one is F, so we can represent both foci. Now let's put any point on the ellipse, for example, right here in this case. And what we're going to do next is measure the distance from here to here, that is, from this point to one focus, and also the distance from that same point to the other focus. Now we're going to add those two distances together, okay? Let's suppose it adds up to 15. I'm just making up a number. Well, it turns out that if you do the same thing with another point that's also on the ellipse, for example, here, the exact same thing will happen. The distance from here to here plus the distance from here to here. It's also going to be the same. I think I said 20, right? Well, it's also going to be 20. So, does that mean this green line measures the same as this yellow line, and it's also going to measure the same as this blue line? Let me see. Allow me. I'll make another one that's going to be, for example, over here. Well, I'll make it red instead. So let's suppose we have another point here, and we do the same thing. We draw a line. It's not turning out well, but I'll do it like this. And another line over here. All right. So it also has to be that if you measure the distance, or, well, the whole length of the red line, meaning this piece plus this piece, it should measure the same as the entire yellow line. And it should measure the same as the entire green line. That must happen, so it states, that geometric place in the plane of any point, where the sum of the distances to two fixed points, called foci, is a constant amount. That's why I say those distances, the sum of the two segments, must always be equal. And well, precisely when this is formed, that's when we say we have an ellipse. Okay, so that would be the correct answer. That's why I tell you that in the end, it was a completely theoretical question. Let's continue with exercise number 62, which says, determine the coordinates of the foci of the hyperbola. And here we are given the equation of the hyperbola. Look, here again, this is something theoretical. It will be necessary for you to memorize the following formula. Let's write x minus h squared over a squared minus y minus k squared over b squared equals 1. This one here is the equation of the hyperbola, but it's horizontal. How do I know it's horizontal? Well, simply by its form. Look, if we have x squared over a squared here, like what I have here, it means it's horizontal, okay? In the case that it was vertical, you'll see that it changes. In fact, I'll let you look up what the equation of the vertical hyperbola is. You'll see that it's similar. It's not the same here. Sorry, but it's horizontal. All right, so with this information, we can already figure out what a squared is, right? Dober, not calculate, but observe what a squared is, which is 16. We also see b squared is 9. Now, what else could we find out? Well, we could also find out how much h is, And we could also find out how much k is. Look, in this case, h and k are used to find the coordinates of the center of the hyperbola. Focus, I'll write the center's coordinates with a capital C, okay? So the center is at coordinates hk in this case. So the center has coordinates that, let's see. We already know that negative h equals negative 4, right? So, if negative h is negative 4, that means h is 4. So we write down 4, comma, negative k equals 1. If negative k is 1, positive k is negative 1. Therefore, we already have the coordinates of the center of our hyperbola. Now we just need to find out where the foci are. And for that, we're going to need a value that's represented by the lowercase letter c. Look, there's a little formula that actually comes from the Pythagorean theorem, which says that c squared plus a squared, that c squared equals a squared plus b squared. This, I insist, comes from the Pythagorean theorem, and I already talked about it in that complete playlist I mentioned, which I have totally free. I explain why this works, but for now, just remember that you have to use the Pythagorean theorem, okay? So let's go ahead and write a squared. In this case, a squared is 16. Then we're going to add b squared. In this case, b squared is 9. And from here, we solve for c. 16 plus 9 is 25. So if c squared is 25, then c is 5, right? Ready? This is lowercase c, and it turns out that lowercase c is the distance from the center to the foci. Okay, so from the center to each of the foci, there are 5 units. In this case, therefore, we could already have a completely finished sketch of our graph, right? Let's see if it fits here. Where is it better? Yes, I think here. I'll make it a bit longer, just in case it doesn't fit. The center is at 4, minus 1. Okay, so we've already seen that it will fit. It might come here quickly, so let's put it over here. Actually, I'm not going to draw the curves. I just want to represent the center and the foci. Okay, so let's see. Here we go. Let's put the center. It says it's at 4, minus 1, 1, 2, 3, 4, minus 1. Here we have the center. We already know c is 5, as I mentioned. C is the distance from the center to the foci. So move 5 to the left and 5 to the right, not up or down. Why? Because it's horizontal due to its shape. Let's go 1 through 5. Here, so there will be one light and the other will be 5 to the right. 1, 2, 3, 4, 5. And then 1 down right. Here we have the other light. Let's check the coordinates. This light has coordinates minus 1, minus 1. Yes, right? Uh-huh. And this one has coordinates, well, over here it was 4, and over here it was 5. So it would be 9 minus 1, right? 9 minus 1. So, what's the answer? Is it minus 1 minus 1? Is that correct? We're finished. Let's proceed to exercise 63, which says, if in the equation there's x squared plus bxy plus cy squared plus dx plus cy plus f equals 0, and the discriminant b squared minus 4c is positive, then the equation represents 1. Let's see. Look, this is also theoretical. The correct answer is if it's positive, it's this one, but then would this one here be the correct answer? I'll tell you why. Look, this right here is called the discriminant. I'm going to assign it a letter. I'm going to use the letter D. Okay, maybe it's not perfect, but I'll use D. If the discriminant is greater than 0, it implies something. Let me show you. I'll put a little arrow to show that we're going to have 2 directions. I'll put it that way. 2 directions. So, does that mean it could be something like this and something like that? This is a hyperbola. Okay. So if the discriminant is greater than 0, it says if it's positive, but it's referring to the same thing. Right. I'll complete the table for you. If the discriminant is 0, we'll only have one direction. What do I mean? For example, we could have something like this, or going down, left, or right, but not 2. Okay, so, just like this, or like this, or like this, or like this. Okay, any of them, I'll just leave it like this. Just something like this. For example, in this case, then, well, this is a parabola. So is this a hyperbola? Is this a parabola? Now, if the discriminant is less than 0 in this case, we're going to say it's closed. How could it be closed? For example, a circle or an ellipse? That didn't turn out well, but these two are for closed ones. So, to sum up, right? If the discriminant is greater than 0, that is. If it's positive, it means there are two directions. If the discriminant is equal to 0, there's only one direction. So, in this case, it would be a parabola. And if the discriminant is less than 0, then it means it's closed. So what would it be then? For a circle or for an ellipse? In this case then, the answer is hyperbola. Anyway, I'll check here in the answers that the guide has. I say the answer is D, which would be for number 63. And here it says yes, the correct answer is D. That's it. So, that way, you could answer quickly just by knowing what I told you about the directions, without needing to do anything else. All right, so guess what? We finished the analytic geometry section, and even I feel happy, because honestly, it is a branch that's a bit complicated to explain. But now let's move on to a calculus problem. This one's a bit easier, honestly. At least the calculus that's coming up isn't that complicated. So don't worry. Look, number 64 says here, find the limit as x approaches a of fx minus gx, given the limits of fx and gx as x approaches a are k and k respectively. It's really a property. So is there a property that tells you the limit as x approaches a of f of x minus g of x? Look, this is a minus, okay? It's equal to the limit as x approaches a of f of x minus the limit as x approaches a of g of x. So it's something like that, as if we were separating them, right? And that's it. In this case, we already have everything, because they're already telling me the value of this limit. In this case, they're telling me it's k, right? So I'm going to write it as minus this other limit. They're telling me that this other limit is minus k. So I end up with k minus minus k. This is the same as 2k, right? So, option C is correct. Easy? Let's move to the next exercise, 65. It says the derivative of the expression how y equals 2x to the 1/2 plus 6x to the 1/3. Well, these aren't expressions. That's a function. So the derivative of the function, you would have to say here, the function is such, right? So, let's go ahead and calculate it in this case again. Obviously, there are formulas that I'll be using, but I'm going to do it in a simple way. Let's see. So let's write that the derivative, which I'm representing as y, is... The first thing I have to do is write the 2, then I'm going to put a parenthesis and bring down the exponent. Okay for this. I'm using some formulas, but I'm doing it implicitly. Okay, so I bring down the exponent, we write the x, and now I'm going to subtract 1 from the exponent. So I get 1/2 minus 1, which is equal to negative 1/2. Sure. What did I do? I lowered the exponent, wrote x, and subtracted 1 from the exponent. That's the rule. Now let's go to the next one. I do exactly the same thing. I have 6, which was already there, and again, I bring down the exponent, which in this case is 1/3, write the x, and subtract 1 from the exponent. And 1/3 minus 1 leaves me with negative 2/3. All right. Now I have the derivative. As it is, it doesn't look like any of the options, so let me work on it a little bit. Here we have 2 times 1/2, that's 1. So I'm going to write it anyway. 1, right? So, 1x to the minus 1/2. Then here we have plus 6 times 1/3, which is 2. 2x to the minus 2/3. This might already be done. Let's see. The first isn't correct, and neither is the second since it has positive exponents. The third also isn't right due to some negatives, so it must be this one. But notice it's still not exactly the same, since they've already moved on. These powers that had negative exponents have already been moved down. So how do I move them down? Well, I put the 1, and since this has a negative exponent, I can put it down here, but now with a positive exponent. I do the same here. Put the 2, then move this below with a positive exponent. Now it's the same, right? U is 1 over x to the 1/2 plus 2 over x to the 2/3. That's the solution. Let's move on to exercise 66. It says the derivative of y equals the natural logarithm of x squared plus 5. Well, here you should also remember that there's a formula for this. I'll write those down so we can find the logarithm's derivative. I'll write the derivative. Let me write it in red. The derivative with respect to x of the natural logarithm of v, I'll write it like this, is equal to, a is going to be the derivative of b. Let me write it with a prime over v. Okay, that's what we need to do. Let's write the derivative of b with respect to v. In this case, it would be v, right? Look, it's the natural logarithm of this, which I'm calling v. So what I have to do, according to the formula I just showed you, is the following. The derivative of this function would have to be the derivative of v. That is, the derivative of x squared plus 5, which would be the derivative of x squared. It's 2x plus the derivative of 5, which is 0. So I'm just left with 2x, right? And that has to be divided by v. That is, by this, which in this case is still x squared plus 5. If it can be simplified, I simplify it. In this case, it can't. So that would be the derivative. So the correct answer is the one in the option. Really, that's it. So just remember, if you are calculating the derivative of the natural logarithm of something, then you put the derivative of that something over the something. That's what you have to do. That's why I say, it's the derivative of that something over that same something. Okay, and that's it. That's all you have to do to be able to differentiate the natural logarithm of whatever you want, or of any function. The slope of the tangent to the curve f of x equal to e to the 3x at point P0, 1 is equal to. Let's see, are they just giving you the derivative definition here? I mean, geometrically, the derivative is the slope of the tangent line to a curve at a given point. That's the definition of derivative from the geometric point of view. So, what would I have to do? So, just take the derivative of this function, right? But in order to take its derivative again, we need to remember what the formula is for differentiating the function e to the v. I'll write it down for you here as well. Look, I'll write the derivative like this. The derivative with respect to x of e to the v. That is, not e to the x. E to the v is equal to e to the v times the derivative of v with respect to x. Let me write v. Okay, even though I should use the same notation, but just so it's clear, well, I'll write it better. I just need to take the derivative of v with respect to x and multiply it. All right, so let's differentiate. In this case, v would be, or, well, v would be all of this. Let me write it here. v is 3x. Okay, so let's differentiate. We get f of x equals. First, it says to write e to the v. So write everything. So let's write e to the 3x. And then we have to multiply this by the derivative with respect to x. Only of v itself. That is, only of 3x. And what is the derivative with respect to x of 3x? Well, it's 3, right? So we end up with just 3 times e to the 3x. That would be the derivative of the function. Now it's asking you to find the tangent line's slope to the curve. At this point right here, all we have to do is take the derivative and then evaluate it here. That is, when x equals 0, because that's exactly the value of x at that point. So I'm going to find, or, well, I'm going to evaluate the function at 0. So f prime of 0 equals 3 times e to the 3 times 0. And this would then be 3 times e to the 3 times 0, which is 0. And this would be the same as 3 times e to the 0. But it's to the 0. Sorry, which equals 1. This is the same as 3 times 1, which is 3. So, the correct answer is option D. Done. We're done. Let's go to exercise 68, it says. All right, let's continue. About integrals. The integral of cosine of 8x with respect to x is equal to. So let's remember again, once more, with the formulas. What is the formula for the integral of cosine of u with respect to u? All right. Well, that's sine of u plus a constant. Okay, in this case, we can't integrate directly like that because that's for the cosine of u. But I have cosine of 8x. So I'm going to say that this right here is my u. All right. And then we're going to do the substitution. So I have that u equals 8x, and from here we can differentiate u with respect to x, right? What's the derivative of 8x with respect to x? Well, it's 8. Let me try a double substitution here. It's a bit unusual. Look, I'm going to move this 8 to the denominator and this dx to the numerator. So I'll have du over 8 equals dx. You're following me with that, right? Perfect. So now I'll rewrite my original integral, which was cosine of 8x dx, and now I'll substitute my variable since everything is set. So I end up with the integral of cosine of u, which is 8x. So here we have a u times dx, but dx, what is dx? It's du over 8. So I'm going to write it like this, times du over 8. I want you to see that what I'm doing is simply a change of variable. So now I can have my integral, but with u, meaning in terms of u, not in terms of x. Why? Because I couldn't integrate directly like that. That's why I'm now writing everything in terms of u. And see, now I can do this, because I can take this 8 out. So I'll have 1/8. The integral of cosine of u du, and cosine of u du, well, now you can integrate it with this formula. Therefore, I'll have 1/8. Of what? The integral of cosine of u du is sine of u plus a constant. So, in brackets, sine of u plus a constant. All right, I'm done. I've already integrated, but I have the answer in terms of u, and the question isn't, is it in terms of u? It's in terms of x. Therefore, I have to go back. So I have 1/8. 1/8 at once that multiplies the sine of u. That multiplies the sine of u. But u is 8x, right? U is 8x plus 1/8 times c. And if I multiply 1/8 by a constant, well, it still gives another constant? Do we agree that's another constant? I'll call it c2, so the answer is 1/8 sine 8x plus a constant. c2 can also be c3k m or anything you prefer. So that's the solution? So this is the correct answer, right? Let's see. It's 1/8 sine of 8x over 8 plus c. Yes, because this one has a negative and this one is missing it. No, these aren't it. This is the correct one. All right, we're done. Here's the solution. Let's move on to the last exercise. It's asking us to solve this indefinite integral again. I won't write the formula again, but remember, the integral of e to the u du is that one. I hadn't written it for you. Sorry, I'll write it now. Let's see. I'll write it for you. The integral of e to the u du, let's see. E to the u du is equal to e to the u plus... Sorry, I hadn't written it for you. I was thinking yes, e to the u plus c. That's the formula we'll use. Look, we don't have exactly that, so we have to try to get to something like what I have here. And again, we're going to get there by making a change of variable. In this case, I'm going to say that everything I have up here is u. That is, x squared plus 4x plus 3 is u. So I'm going to write it here. U is x squared plus 4x plus 3. We differentiate u with respect to x, and then I get the derivative of x squared is 2x plus the derivative of 4x is 4. Look, let me go ahead and do the following here. I'm going to write that do is equal to. I'll factor out a 2 here. So I get 2 times what? So 2 times what equals 2x, that's x. And 2 times what equals 4, that's 2, right? I'm factoring this one, okay? I'll move the dx here. Does it look like this? So du is 2x plus 2 times dx. Why am I doing all this? Because look, I have that right here. Here, I have x plus 2 dx, which is this. I'm just missing a 2. But guess what? I'm going to add it. I mean, I'm going to put a 2 here, okay? I'm going to multiply my integral by 2, but then I have to divide by 2. That's the same as multiplying by 1/2, so the integral stays the same. Now I'm doing all of that. Because look, 2x plus 2 dx, I mean, between this and what I have here, between these two, they already form my u. Look, 2 plus 2 dx. All of that is du. Therefore, I can already make my variable substitution. Let's see what was left out. Well, I'm not using this 1/2, so I'm going to include it. So I end up with 1/2 of the integral. From what? From e, which is over here, to what? Well, to u. All of that was u. By what? By du. Why only by du? Well, because between this here and this here, which is this over here, it's du. For that reason, I'm left with only 1/2 from e to u for all of this, which is du. And this formula, well, it's already over here, right? Or, well, not that formula, but this integral that we've arrived at. So can I integrate now? So I'd have half the integral of e to the u, du, which is e to the u plus a constant. I'm not adding the parenthesis here anymore, because half times the constant is still just another constant. That's it. We have the solution to the integral. Finally, I just go back to my original variable, which was x, right? So I get 1/2 of e to the u plus c, where u is x squared plus 4x plus 3. So I go back to x squared plus 4x plus 3. And well, finally, plus a constant, this one right here, and that will be the solution. And that's it. Which option is it? 1/2 e to the x squared, right? Okay, that's it. Let's see, the others, no, right? Let's see. This one doesn't have 1/2. It has a negative. Yes, that's correct. That's it. We're done. If you found this video helpful, please subscribe to the channel. I'm doing this with a lot of pleasure to be able to support all of you, and I also don't want this to become paid content. So it's important. Please support me by subscribing to the channel if you've benefited from this video or are studying with this material. And also, since I'm taking advantage of your trust, please share this video with someone you think it could help. Goodbye. I'm Jesus Grajeda Rosas. See you next time.